So in the previous lectures, we have learned how we can model and model this type of solar mounted steel structure, how we can apply the dead load. And in this lecture, we shall learn how we can apply the wind load and what are the practical aspects for which we should consider the wind load. So considering this as an example, so basically on all these members also the solar panels will be mounted. So when the wind will flow along this particular direction, the number one resistance that wind shall face shall be the surface area of all these solar panels, and the second thing is the surface area of all these structural members here. So let us suppose the vendor says us that he wants us to analyze and design the wind force for 100 kg per meter square. So we can add intensity of 1 kN per meter square, that is 100 kg per meter square, up to the height of 10 meters, and then we can apply factor of 1. So we can assign to view and yes. So as I had also told you earlier also that there shall be two parameters. One shall be when the wind will flow along this direction, the solar panels will offer the resistance to the flow of wind, and the number two will be these members. So we shall apply wind load on as a solar panel surface area as well as on the steel structure surface area. So to start with, what we need to do here is that when the wind load will blow along this x direction, so basically the only resistance shall be the surface area of the structural steel members itself, because when wind will flow along this direction, the solar panels surface area is only in this particular area, so that is a negligible parameter. So what we need to do here is that for x direction we can just go to wind load and x and open structure and add. So with this we can apply wind load along the x direction. Now when we are talking about the wind load along the z direction, so wind load along z direction is somewhat complicated because we need to apply the wind load only on these members, vertical members, and on all the horizontal members as per the, and it's like a flow load. So what we need to do here is that 100 kg per meter square is the wind intensity and 1.5 meter is the effective span. So 100 kg is nothing but 1 kN per meter square, so 1 into 1.5, so it shall be 1.5 kilonewton per meter UDL along the z direction. So we shall go to the member load and global z direction and 1.5, and then left click on add here. So we need to select those members again. So here we can see that how we can apply the wind load intensity along the z direction. So there is this another approach in which we can apply the wind load as a flow load distribution. So that also I want to teach you as another practical aspect. Please note that that is just another method of applying wind load. So we can select all these members here, and then what we can do here is that we can just go to the, let us suppose we create another imaginary case. So here go to the flow load and then group, and then we can select minus 1.5, inclined floor, and direction shall be the global z direction. So this is another manner in which we can apply the wind load along this particular direction here. But the disadvantage of following that approach is that whatever solar panels area is coming here, that is after this main beam, it shall not be accounted for with this manner, but that also can be accounted by modeling a very low stiffness beams here like this. So when we can just model these beams, and then automatically the flow load shall be distributed, but that is just another hypothesis, I must say. So this approach is also not bad, because basically whatever loading shall be are being coming here, that are only acting on these members, because we cannot say that like this member and this member is at the same level here. So basically whatever loading or whatever wind loading shall come, it shall apply as a uniformly distributed load on all these beams here. So now wind load is also done, but we have not considered the wind load on these column surface areas. So what we can do is that we can give the range for this wind load. So basically the z coordinate is 0 here. So we can go to wind load here, z factor, and we can just select the z as minus 0.1 to plus 0.1. Here we need to apply open structure. So with this approach we can just apply the wind load, and what we can do here, we can apply the Y range also. So Y range we can name it as maximum 0.74. So after that what we can do here is that we can apply wind load on along this plane also. So this was just a simple approach with which we can apply the wind load. Or what we can do on the conservative side is that we can just delete this range. So that wind load shall be applied on all the members here, because basically there's also another concept that maybe wind can go like this, and then it may act on these members here. So to consider surface area for wind which may go down and act on all these members, so I shall propose you that we can apply with this approach also. And let us select the direction here. So the direction for wind load along z direction is, now we are basically considered the wind load along minus z here. So this is also correct and this is also correct. So after that basically there is no need of applying live load here, because basically no one will stand on all these solar panels here. But as a just hit and trial, what we can do is that we can apply 20 kg per meter square live load also. So for applying live load, so if 20 kg live load is there, so it's basically nothing but 0.2 into 1.5, so 0.3 kilonewton per meter square again, sorry, per kilonewton per meter UDL again. So we can just go to the editor file here. So we can just repeat this command here in under the live load section. So with this approach we can just apply the live load also. And after that, so basically we are like checking this whole structure for 60 kg per meter UDL. So that is also very high, or we can just reduce it to, let us say, 0.15 itself, because that much loading shall not act on the solar panel supporting steel structures. So after that what we can do is that we can apply the auto load combinations also as per the Indian codes and general structures and generate loads. So we can just go to the we can create a repeat load cases also for more precision. And now basically all the things are considered. So properties are correct, specifications, specifications, we can offset these members here, because basically these members, this member is resting on this and then this member is resting on this. So there is a lot of height difference here, and when we will see the 3D view here, it is not much matching with what we are taking here as a reference. So first of all we need to offset this particular member here. the height of this member is 100 mm. So we need to offset this member by vertically by 100 mm. Beam offset and y as 0.1. So left click on add here and then offset and y as 0.1. Similarly, we can assign offset to these members also. After that, we need to offset this particular member also. So 100 plus its depth. So this member is also of 100 mm depth. So we need to offset these members by 200 mm. Sorry, these members here. So what we can do to save our time is that we can just offset and y as 0.2 and end point and y as 0.2. And after that, what we can do is that we can just select the properties of all these members from editing list, and then we can go to the specification here. So this is just a simple step that we can do, and when now we will check the 3D view. Let us check it whether it is correct or not now. So here we can see that there is this problem here. Now let us check whether this arrangement is correct or not. So now it is correct. And then after that we need to check this arrangement also. So this in this arrangement now there is a gap. So basically we need to offset this arrangement by 0.1 only. Let us check it whether this arrangement is correct or not. Still it is 50 mm problem here. So add 50 mm here. So now it is correct here. So now this member is resting on the top of this particular member. So with this like simple approach, we can change the specification and make the structure more realistic, like what we shall construct in the practical. So now the specifications are also done, properties are also done, support is done, loading and loads combination is done, and material is also done. So after that we can go to the analysis command and we can add perform analysis here. And after that we can go to the design and steel. Here we need to select IS 801. So here we can select IS 801 and then we can go to define parameters. So after that we can select this yield strength of steel. So here we can select 300 MPa. LZ we can select for this particular member here. So LZ we can take it as 3 meters. So here we can just assign to view here. And for all these members we need to assign LZ of 3 meters. And after that we need to go to the check code command, and if you want to calculate the weight of the structural steel, we can go to the steel takeoff command also. And then let us check it whether now there's this one more thing that we should always do, that we should always give load list command after the perform analysis. So load list from 5 to 14. And then after that we can go to the analyze. Let us check whether the model is correct or not. There is this one error here. We can change it to single channel here. So as I discussed with you earlier also, that maybe these members may not be designed as per the American standards here. So these type of things to happen in start, that only particular design course. So because actually the reason is that we are designing as per the Indian standard, so the start is expecting us to take the properties of the cold form structural steel as per the Indian standards itself. So what we can do here is that we can go to the section database again, and we can go to cold form steel, Indian cold form, and we can select channels here. So we can take the higher size channel here, so we can left click on add here. So let us now check it whether this can be analyzed or not. So now the things are correct. So here there are basically no warnings here, and it is showing us the steel design results also. So let us check what members have failed and what members are passed. So select by specification and all failed beams. So basically all the beams are passing except this main particular beam here. So in this beam it is showing very high utilization ratio along the minor axis, that is 8.5. so it is basically showing us the ratio of 2.47 here, and here it is showing the ratio as 0.9. So what we can do with this approach is that we can increase the size of this member, but let us check the behavior of other members also. So if you see the bending moment diagram here, so bending moment diagram is correct, that it should for the beam along this direction it should go like this, and for the beam along this direction it should definitely go like this. And for the columns here, they are highly over designed, so we can, first of all we should stabilize the upper structure. So this member is correct, but this member is showing us some problem here. So for 290 CS 53.5 is used.